An LNG compressor does not become unstable only because the machine is defective. It often becomes unstable because several individually correct control loops begin fighting each other. The Antisurge controller opens recycle to protect the compressor. The capacity controller increases speed to recover throughput. The turbine governor reaches its power limit. The process controller moves the Joule Thomson valve to restore temperature. Every controller is responding correctly to its own measurement, yet the combined refrigeration train begins to hunt. That is the real control problem in an LNG plant. You are not controlling one centrifugal compressor. You are controlling a tightly coupled thermodynamic system containing propane refrigeration, mixed-refrigerant compression, gas turbines, recycle valves, separator drums, Joule Thomson valves, and the main cryogenic heat exchanger. A disturbance in one section changes operating conditions everywhere else. In a propane pre-cooled mixed refrigerant process, the C3 system pre-cools the feed gas and mixed refrigerant. The MR system then provides the lower temperature refrigeration required inside the main cryogenic heat exchanger, or MCHE. LNG production therefore depends on how safely and efficiently the C3 and MR compressors are loaded, unloaded, protected, and coordinated with the process. The weakness of conventional compressor control is fragmentation. Antisurge control operates as one package. Compressor capacity control operates separately. The turbine governor follows its own limits. Process controllers move valves based on pressure and temperature. Advanced control sends optimization targets from above. The drawing may look organized. The plant may not behave that way. When ambient temperature rises, gas turbine power falls. When feed composition changes, compressor head and power change. When production demand falls, refrigeration duty falls. When storage or tanker constraints reduce plant rate, the compressors must operate at part load. When feed gas is lost, MR suction temperature can collapse. If the controllers are not integrated, operators are forced to repeatedly adjust turbine speed, JT valve position, and compressor loading manually. That approach depends on operator skill, creates inconsistent responses, and hides poor control design behind manual intervention. The correct engineering objective is an integrated turbomachinery control system. An integrated system coordinates anti-surge protection, compressor capacity, driver control, load sharing, constraint control, process regulation, and production optimization. Its job is not simply to keep the machine away from surge. Its job is to maximize useful refrigeration throughput while keeping the complete compressor driver process system inside a verified safe operating envelope. That envelope is bounded by several limits. For the compressor, you have the surge limit, choke limit, minimum speed, maximum speed, casing pressure constraints, process limits, and control margins. For the gas turbine, you have minimum and maximum continuous speed, shaft power limits, exhaust temperature limits, air compressor discharge pressure limits, and overspeed protection. The maximum plant rate is not the theoretical compressor capacity. It is the highest stable throughput achievable without violating any machinery, process, or thermal constraint. The challenge becomes greater because an LNG train operates in several distinct modes. During a cold start, the rotating equipment has been shut down for an extended period and the MCHE is relatively warm. Refrigeration must be introduced gradually. The exchanger must cool at a controlled rate to prevent excessive thermal gradients and structural damage. During a warm start, the MCHE remains cold enough for a faster restart. Compressors are typically brought to minimum governing speed with recycle valves open before controlled loading begins. During part load operation, production is reduced because of feed limitations, tanker delays, process restrictions, equipment problems, seasonal demand, or warm weather. Part load is where poor integration becomes obvious. Recycle valves operate continuously. Capacity controllers attempt to reduce throughput. Series compressor stages influence one another. Process pressures begin oscillating. The operator eventually transfers control loops to manual simply to stop the hunting. During maximum production operation, the objective reverses. The control system must push the train toward its available machinery and process limits without crossing them. During normal shutdown, the compressors must be unloaded gradually. During an emergency, they must be unloaded rapidly enough to prevent surge, overpressure, or equipment damage. One fixed, independent loop strategy cannot manage all these operating modes effectively. Start with anti-surge control. Refrigeration compressor suction conditions do not remain constant. Pressure, temperature, speed, gas composition, molecular weight, and variable vane position may all change. The surge control algorithm must remain valid despite those changes. For a simple machine, engineers often think in terms of a surge limit line. For an MR compressor, one line may be inadequate. The machine may have a surge limit surface because the true surge boundary changes with speed, suction conditions, refrigerant composition, and vane position. If the controller uses an excessively conservative line, the plant loses turndown and wastes power through unnecessary recycling. If the line is optimistic or inaccurate, the compressor may operate inside the unstable region. The anti-surge controller must calculate the real distance between the operating point and the surge boundary, then maintain an appropriate control margin. Protection without excessive recycle is the objective. Side-stream compressors introduce another problem. A multi-stage C3 compressor may receive propane vapor at intermediate stages. The internal flow entering a side-stream stage may not be directly measurable. You cannot protect that stage using only the main suction flow measurement. The controller must calculate effective stage flow using mass balance, side-stream measurements, pressure, temperature, and compressor similarity relationships. If this calculation is poor, an internal stage can approach surge, while the total compressor flow still appears acceptable. Series compressor stages also interact dynamically. Consider an LP and HP compressor operating in series. The LP recycle valve opens. Flow leaving the LP compressor falls. The HP compressor immediately receives less flow and moves towards surge. If the HP anti-surge controller waits until its own operating point approaches the control line, its response may be late, aggressive, or oscillatory. Dynamic decoupling is the stronger strategy. When the LP recycle valve opens, the control system predicts the resulting downstream flow reduction and opens the HP recycle valve by a calculated feed-forward amount. The HP anti-surge controller then corrects only the remaining error. This is a fundamental control principle. Do not wait for a predictable disturbance to become a measured problem. The same method applies to multi-stage C3 compressors, although the interaction gains must reflect the actual influence between stages. Not every downstream stage affects every upstream stage equally. Anti-surge control must also handle automated loading and unloading. During startup, recycle valves should close in coordination with increasing speed and rising process demand. During normal shutdown, the valves should reopen gradually. During a major process upset, they must open quickly enough to unload the compressor before the operating point crosses into surge. But recycle valves are not used only for surge protection. Constraint control may require recycle action even when the compressor is well away from the surge limit. For the C3 compressor, first stage suction pressure may need to remain above atmospheric pressure. If it drops too low, process instability, air ingress, or machinery problems may occur. The first stage recycle valve may therefore open to maintain suction pressure above a safe minimum. For the MR compressor, loss of feed gas to the MCHE may cause LP compressor suction temperature to fall sharply. The recycle valve may need to open on low temperature constraint before machinery or process limits are violated. Discharge pressure may also require limitation to protect the compressor casing, prevent flare valve opening, or avoid process overpressure. This means a recycle valve opening does not automatically indicate an imminent surge event. It may indicate a suction pressure constraint, temperature constraint, power limit, discharge pressure limit, poor load sharing, or incorrect compressor map configuration. Every unnecessary recycle movement has a cost. The compressor consumes shaft power, but part of the compressed gas is returned to suction instead of producing useful refrigeration. Fuel consumption rises, refrigeration capacity falls, LNG production declines. Now consider capacity control. The capacity controller adjusts compressor throughput to match refrigeration demand. For the C3 compressor, the principal controlled variable is often first stage suction drum pressure. The intermediate propane drum pressures are thermodynamically linked to that first stage pressure. If it floats, propane pre-cooling duty changes continuously. The MR system then compensates for the changing pre-cooling load, creating stronger interactions between the refrigeration cycles. The engineering target is usually to maintain the C3 inlet pressure at the lowest safe and stable value that supports efficient process operation. For the MR compressor, capacity may be controlled using the pressure ratio between the HP separator and the LP knockout drum. This ratio represents the compression duty imposed by the mixed refrigerant circuit. With a variable speed driver, compressor throughput is primarily changed by varying speed. If the compressor also has variable guide vanes or adjustable geometry, speed and vane position should be sequenced. The purpose is to expand the usable operating envelope, preserve efficiency, and maintain stable operation at low plant rates or reduced turbine power. Capacity control must always respect constraints. When production demand increases, the controller cannot continue raising speed indefinitely. It must recognize turbine power limits, compressor speed limits, casing pressure limits, discharge pressure limits, choke boundaries, and process temperature constraints. The control objective is not maximum demanded throughput. It is maximum permitted throughput. Series compressors with separate drivers require coordinated load sharing. It is poor operation when the LP compressor reaches its power limit while the HP compressor operates close to surge. The reverse condition is equally inefficient. The load-sharing controller should distribute duty so that the stages approach their limiting boundaries in a coordinated manner. Stage power, pressure ratio, speed, surge margin, and available driver power can all be used as load-sharing variables. C3 compression is more difficult because side stream flows and stage pressure ratios are significantly different. Equal speed does not mean equal loading. Equal power does not necessarily mean optimum loading. The correct distribution is the one that maximizes stable throughput while keeping both stages away from their critical boundaries. The most common control conflict occurs when capacity control and anti-surge control operate independently. Imagine that production demand is reduced. The capacity controller lowers compressor speed. Flow decreases. The anti-surge controller detects reduced surge margin and opens recycle. Recycle raises compressor suction pressure. The capacity controller now sees suction pressure above its target and increases speed. Higher speed increases flow, so the anti-surge controller closes recycle. Suction pressure then falls again. The sequence repeats. The plant begins hunting because one controller continuously creates the error that activates the other. A common field solution is loop detuning. Engineers reduce controller gains until the oscillation becomes less visible. That may suppress hunting, but it produces slower response, poorer disturbance rejection, and wider deviation during normal operation. Detuning does not remove the interaction. It merely weakens both controllers. Dynamic decoupling is the correct solution. The capacity controller must account for recycle valve movement. The anti-surge controller must understand compressor loading demand. Their actions must be coordinated so that one loop does not unknowingly reverse the action of the other. Integrated control produces stability without sacrificing loop performance. Automated compressor loading is equally important. Manual loading depends heavily on operator judgment. The operator must coordinate turbine speed, recycle position, stage interaction, suction pressure, driver loading, process temperature, and MCHE cooling rate. In a multi-stage train, even a small sequencing error can delay startup or push one stage towards surge. An automated loading algorithm increases throughput at a controlled rate, closes recycle valves in sequence, and transfers the governor from local to remote control without abrupt changes. An automated unloading algorithm reverses the process smoothly when the train is taken offline or placed in standby. For the MR system, the loading rate must also respect MCHE thermal constraints. A compressor may be mechanically capable of increasing flow quickly, but the exchanger may not be able to accept that thermal change safely. Rapid recycle valve movement or fast compressor loading can produce sharp temperature fluctuations inside the MCHE. Protecting the compressor while damaging the heat exchanger is not successful control. Governor integration is therefore essential. During startup, the turbine governor normally operates in local mode and brings the train to minimum governing speed. Once the refrigeration system is ready for loading, the capacity controller sends a remote speed demand. At high production, the capacity controller may drive the turbine toward its available power limit. When that limit is reached, integral windup must be prevented. Without wind-up protection, the capacity controller output continues accumulating while the governor cannot increase speed or power. When the constraint clears, the stored controller demand can create a large overshoot. When refrigeration demand decreases, the system must detect the lower requirement and drive the turbine away from the power limit. Transfers between local and remote modes, or between capacity control and power constraint, must be bumpless. A change in control mode should not create a step change in speed demand. The governor must be fast, deterministic, and closely coordinated with compressor protection. Anti-surge calculations may require execution within approximately 40 milliseconds. Governor functions may require execution near 20 milliseconds. Slow supervisory logic in a general-purpose DCS cannot replace high-speed turbomachinery control. The control architecture must also be fault-tolerant. Loss of one pressure transmitter, temperature transmitter, or flow signal should not immediately leave the compressor unprotected. Signal validation, transmitter voting, calculated fallback values, and duplex control architecture improve availability and reduce unnecessary trips. Integration must extend beyond the compressor and turbine. The regulatory control system manipulates offtake valves and JT valves around the MCHE. JT valve movement directly changes mixed refrigerant flow, pressure ratio, and compressor loading. During startup and part load operation, MR recycle valves may already be active. If the JT valve moves aggressively without coordination, it can push the compressor towards surge or choke. The regulatory controller, capacity controller, and anti-surge controller must therefore exchange operating information and respect common limits. Above them, an advanced control system may optimize LNG production and generate set points for the refrigeration train. But optimization must remain outside the high-speed protective layer. The advanced controller determines the desired operating target. The Integrated Turbomachinery Controller determines whether that target is safely achievable. The optimizer should never override machinery protection. Finally, do not assume that the compressor map used during design perfectly represents the installed machine. OEM curves may differ from field behavior because of gas composition, piping configuration, suction conditions, instrumentation accuracy, fouling, wear, or long-term degradation. The surge limit parameters should be verified under actual installed conditions, particularly during part load operation and retrofit projects. Field testing must be carefully planned. Testing an MR compressor with the MCHE in the operating loop introduces serious thermal risk. A surge event or flow reversal can create abrupt temperature changes in the exchanger. The purpose of testing is not to demonstrate how close the machine can be pushed toward damage. The purpose is to establish a defensible surge boundary, verify instrumentation, validate the control algorithm, and define a reliable operating margin. When LNG compressor control is fragmented, operators spend their shifts chasing disturbances. Speed set points are repeatedly changed. JT valves are moved manually. Recycle valves operate more than necessary. Turbine trips increase. Restarts become slower. Recovery after a process upset becomes uncertain. When the control system is integrated, the behavior changes. Compressors load and unload smoothly. Series stages share load intelligently. Recycle movement is minimized. The gas turbine operates close to its useful power limit without violating machinery constraints. The MCHE cools at an acceptable rate. Process disturbances are absorbed before they develop into trips. That is the central engineering lesson. Anti-surge protection, compressor capacity control, turbine governing, load sharing, process regulation, and production optimization are not independent control packages. They are parts of one dynamic system. You do not maximize LNG production by pushing every controller harder. You maximize production by ensuring that every controller understands what the others are doing, anticipates dynamic interactions, and continuously drives the refrigeration train toward the highest stable throughput inside a verified, safe operating envelope. That is the difference between controlling a compressor and controlling an LNG plant.